Hello friends, welcome back to our 10th lecture on the detection and estimation theory. And we were talking about the matched filters. In this lecture, we are going to look at some more properties of the matched filters. And let's go ahead. So let me do a quick revision of what we were discussing in the last lecture. So in this kind of problem, we have again two hypotheses, hypothesis 0 and hypothesis 1. So this is about the known signal in noise problem. Okay, so the signal is known. So the hypothesis 0 is just the noise, and the hypothesis 1 is the known signal plus the noise. Now the noise is we have taken it to be the white Gaussian noise, okay, with mean 0 and variance sigma square. Okay, and the correlation between the noise is 0. That means the noise is uncorrelated. Okay, noise is uncorrelated. And for this kind of a case, we figured out the NP test statistics. So the Tx came out to be summation and goes from 0 to capital N minus 1 x of n s of n. So this was our test statistics, and if it is greater than some threshold lambda dash, then we detect h1. If it is less than this threshold, we detect h0. And then to solve this problem, we had drawn a model wherein we take input xn and then we pass it through a finite impulse response FIR filter with impulse response hn, and hn is defined as s of n minus 1 minus n for n between 0 and capital N minus 1 and 0 otherwise. And then we take this output yn, we pass it through a switch. The switch is closed at n is equal to capital N minus 1, and then we pass the output of this switch to a threshold detector. If it is greater than lambda dash, we detect h1. If it is less than lambda dash, we detect h0. Alright, and this hn was our matched filter. This was an important thing that we observed here. And the main property of this matched filter was that it maximized the SNR at the output of the filter. All right. Now we are going to look at some more performance aspects of the matched filter. So in the classical estimation theory, we look at such kind of detectors which maximize the probability of detection such that the probability of false alarm is equal to alpha. Okay, so this is our job in the classical detection theory. So to get that, let me first figure out what is going to be the distribution of this Tx, the test statistics, in under both the hypotheses. So I'm going to first figure out what is the probability of T of x given hypothesis 0 is correct, and what is the probability of Tx given hypothesis 1 is correct. So you can see here if we look at the test hypothesis under hypothesis 0, this is the probability. So let me first write what is Tx here. Tx is equal to summation xn times Sn, right, Sn times xSn, n goes from 0 to capital N minus 1, and here in under hypothesis 0, my xn is wn. Okay, so this is n is equal to 0 to capital N minus 1 wn times Sn. Now you can see here, please note here that wn are white Gaussian noise, so these are Gaussian distributed with mean 0 and variance sigma square. So if you take the sum of Gaussians, Sn is a constant for each time interval. So if you take the sum of the Gaussians, this is again a Gaussian distribution. Okay, this we all know. So this is again a Gaussian distribution, and the mean of this Gaussian distribution, mean of this Tx under hypothesis 0, if you see, this is equal to, you can write the expectation of this summation and you take the expectation inside, it will be expectation of Wn, which is equal to 0. So the expectation of this particular quantity here is 0. All right. Let me also get the variance of this Tx under this hypothesis 0, H0 hypothesis. So this is what? This is the expectation of the test hypothesis minus the expectation of test hypothesis under obviously H0. All right, and I take a square of it. So this is the definition of variance. So this we know from our earlier thing, it is 0. So this turns out to be the expectation of summation Wn Sn whole squared, and if you of summation, so the first terms will be Wn square Sn squared, n goes from 0 to capital N minus 1, plus the other terms will be the double summation, the cross terms. Let me write it something like this: I is equal to 0 to capital N minus 1, j is equal to 0 to capital N minus 1, j not equal to I, Wi Wj Sij. Okay, now let me take the expectation inside to see what it yields. So this will be expectation summation W square n S square n plus double summation over I and j not equal to I. This will be expectation of Wi Wj. Si and Sj are constant, so I can take it outside. All right. So if you see this expectation here, because the noise is uncorrelated, so this expectation comes out to be 0 here. So what we are left with is the expectation of this particular quantity, which we can write it as summation n goes from 0 to capital N minus 1, expectation of W square n times S square of n. Now the expectation of W square n is sigma square. So this is sigma square times summation n goes from 0 to capital N minus 1 S square n, and this we know this is the signal energy, which we have defined it to be E. Okay, so E is the signal energy. So this is the variance of the test hypothesis under the test statistics under the null hypothesis. So the test hypothesis under null hypothesis is distributed as a normal distribution with mean 0 and variance sigma square times the energy of the signal. All right. Now let's do the similar exercise for the test hypothesis under test statistics under the alternate hypothesis. So Tx under H1 is given as the summation again xn Sn, n goes from 0 to capital N minus 1. This is equal to summation S square n plus Wn Sn, summation n goes from 0 to capital N minus 1. So I have replaced xn by Sn plus Wn. Okay, so xn is replaced by Sn plus Wn here. So this is what we get. Again, you can see here that this summation S square n, this is a constant, Wn's are Gaussians, and this is the sum of the weighted Gaussians. So this whole is again distributed as a Gaussian. Okay, again a Gaussian with, let's find out the mean and the variance for this case. So what is the mean of this? The expected Tx under hypothesis H1, if I take the expectation, what we are going to get is expectation of this plus expectation of this. Now we know from the earlier exercise expectation of this is 0. The expectation of this will be the summation s square n, and that we know it is the energy of the signal. Okay, so we got to know that the expectation is E. What about the variance of Tx? You can do the similar exercise as in the previous case, and the variance comes out to be same as sigma square E. Okay. So the variance turns out to be sigma square E. So our test statistics has a distribution of n with mean 0, variance sigma square E for hypothesis H0, and under hypothesis H1 the mean is E, variance sigma square E. Okay, so this is our distribution of the test hypothesis. All right, now what we do in classical detection theory is that we try to maximize the probability of detection such that the probability of false alarm is equal to alpha. Now what is the probability of false alarm here? Probability of false alarm is the probability that Tx is greater than lambda dash under hypothesis H0. So this is equal to, so this is what the integral from gamma dash to infinity. I can write the distribution of Tx under hypothesis 0, which is 1 over 2 pi sigma square E under root exponential of minus Tx is I'm writing as T square over 2 sigma square E dt, and this is equal to, in Q function I can write it as gamma dash divided by under root of sigma square E. Okay, so this is my probability of false alarm, and if I equate it to alpha, I can get from here gamma dash, the threshold, to be Q inverse of alpha times under root of sigma square E. Okay, so this we get as our threshold value, and from here we can also get what is the probability of detection. This is equal to the probability that my test statistics is greater than gamma dash under hypothesis H1, which I can write it as gamma dash to infinity. Now I'm going to write the distribution of the test statistics under H1, which is 2 pi sigma square E exponential of minus T square over 2. Now here mean is E, so this becomes T minus E whole square over 2 sigma square E dt. And in our Q form notation, this is Q of T minus, sorry, it's not T, it's lambda dash minus epsilon divided by under root of sigma square E. And I can sorry, this is not lambda dash, this is gamma dash, sorry, and I can replace gamma dash from here, so I get this to be Q of Q inverse of alpha minus epsilon over sigma square E, so this is E, sorry, not epsilon, this, which I can also write as Q of Q inverse of minus under root E over sigma square. Now if you remember from our earlier lecture, this particular quantity is called as the SNR. Alright, so I can write this PD to be Q of Q inverse of alpha minus under root of SNR. So one thing to note here is that as we increase the SNR, this particular quantity is going to decrease, and you can see PD increases. Okay, so this is one particular relation which is very intuitive also. As you keep on increasing the SNR, you also get a better performance of the detection probability. All right. So there is something called as the processing gain. So there are a couple of terminologies that we are going to discuss now. The first one is called as the processing gain, and this is the improvement in SNR compared to a single data versus n data set. Okay, so what's the improvement in the SNR compared to the when we have just a single data versus when we have n set of data? So I can write this. So I'm just taking for a simple DC case, DC in wide Gaussian noise. So in DC case, your SN is equal to A. So in the first case, let me call it as eta 1. Eta 1 is when I'm just taking only 1 point. So if I'm taking just 1 point, my energy for that 1 point is summation S0 square, and only 1 point is there, so it is S0 square, which is A square in this case. So this becomes A square over sigma square. This is the SNR when we are just taking a single data. When we are taking n data, when we consider n data points, then my energy becomes summation Si square. I goes from 0 to n minus 1. Si square is A square, so this becomes n times A square. So let me write it as like this. This becomes n times A square over sigma square. So my processing gain is given in dBs, and I can write it as 10 log 10 n over n1, which is equal to 10 log 10 times n in dB. So this is my processing gain. Again, you can also figure out the deflection coefficient for this case. So the deflection coefficient is d square is defined as the expectation of the test statistics under hypothesis 1 minus the expectation of test hypothesis under test statistics under hypothesis 0 square time divided by the variance of the test hypothesis under any of the hypothesis. Let me write it H0. Now expectation of Tx in under H1 is E minus 0 whole square divided by this is sigma square E, and this is equal to E over sigma square. Okay, so my deflection coefficient also we have figured out, it is E over sigma square. Alright, so here I am ending the discussion on matched filter under the assumption that the noise is wide Gaussian noise. Noise is uncorrelated. In the next lecture, what we are going to look at is what happens when the noise is colored. So before that, I am going to give you a small problem which you can try it at your places, and you can tell me, you can try solving it and tell me the answer. So this is an exercise for you. So exercise problem is, again we have two hypotheses H0 and H1 with the same things. Xn is here the noise, and the H1 hypothesis is signal plus noise. Again n goes from 0 to capital N minus 1. Now, rather than noise being a white Gaussian noise, it is a colored noise. Colored Gaussian noise. So what is the property of colored Gaussian noise? That means the noise samples are correlated. So I can denote W as a normal with mean 0, and the covariance matrix is given by C. C is called as the covariance matrix. Alright, so the elements of C, the m cross nth element of C is the covariance of Wm and Wn. Okay, so this is given as the expectation of Wm times Wn, and another way of denoting it is something like this. So this C is the covariance matrix, which tells how the different noise samples are correlated. And a hint I am giving to you, the likelihood function under this case is given by this formula: 1 over 2 pi power n by 2 determinant power half of C is the covariance matrix, exponential of minus half x vector minus s vector transpose C inverse x vector minus s vector. Alright, so I've also provided you the likelihood probability, and under this assumption that the noise is colored, you have to figure out what is going to be my L of x, the likelihood ratio test or the test statistics. What is going to be my test statistics under this case? Thank you very much.